So this is the Constant Velocity Lab for Physics by myself, Mantalis Benavichus. So the purpose of the lab was to analyze the motion of a tennis ball that was moving in constant velocity, and we were pretty much just comparing the reality versus the theoretical. So we were looking at actual data versus the theoretical graph that we found. And the setup here was we took a recording of tennis ball rolling across the table, so we have a side profile view of that. And we used Newton's second law to determine that it was in fact following a constant velocity. The real data was using Tracker software, and the theoretical simulation was using GlowScript. The theoretical and the actual didn't really match 100% simply because the real one possesses friction and other forces that we were considering negligible since we are considering it to have a constant velocity. So Newton's second law is explaining why this is in constant velocity, and that's simply because it's relating the acceleration to the net force. Now, the net force equals mass times acceleration, where delta v over delta t, or change in velocity over change in time, is equal to the acceleration. And net force divided by m is therefore, or mass, is therefore equal to delta v over delta t, which pretty much just says that since there's no net force that we're saying is acting on it in the x direction, or y direction really, that means that there's no change in velocity and it's in constant velocity. Because here the acceleration is 0, so the net force is 0. And yeah, that's why it's in constant velocity. So the assumptions were the mass is 0.056 kilograms, with the radius being 0.0327 meters, which we found using data from Google. The angle of the video showed no change in the y or z position vectors, and there's no net force acting in the y direction, simply because the force normal and the force of gravity are counteracting each other. So net force equals 0 in the y direction, and the friction was negligible in the x direction. So we're saying that it's in constant velocity in the x direction. So that was acting upon the system, which is the tennis ball, and the surroundings were simply the table with no net forces acting on it. So the tracker data that we found was this, and we used that simply by having the video recording up and then simply taking like little time interval, like position interval clicks on my keyboard, with my mouse, and pretty much just doing that along multiple position points to get this data. And you can see that the graph of the position versus time is relatively linear, which shows that it is in constant velocity. So calculated, we're using data from 11.407 seconds to 12.407 seconds because the beginning part was not really moving yet in the video, so it's just like weird. So the change in time was 1 second exactly, and that's what we're going to be using. And the original position of the ball was 0.125 meters in the x direction, with 0 and 0 for the y and z directions. The ball's velocity was therefore calculated to be 0.757 meters per second in the x direction, with the y direction having a negligible change given our data. So then we had to compare this to the GlowScript code. So GlowScript, I needed to go in and change a couple things. Here's all the code for it, but I pretty much needed to change line 32, which has the mass. I needed to change that to be the mass in kilograms of the tennis ball. And then lines 35 and 36 for the original position vector and the velocity vector. And then a little bit of updating later on as well, just to get the correct calculations. So here's the graph for the GlowScript, which pretty much just shows you it's in constant velocity, since it is a linear graph of position versus time for the tennis ball. So when I analyzed the video data in Tracker, made a choice of orientation of the axes. So this would change if I flip the axes, simply because it could change it to be negative versus positive, and therefore it would look just a little bit different. And then for the second part, is it possible for you to say how many pushes and pulls are added together to get that? So you can't really see how many different forces are acting on it. You just know that it is 0. So conclusion, there's similarities and differences between them. However, it's relatively the same, and possible error was simply me misclicking and negligible forces actually acting. And then I gotta figure out how to stop recording.